So today we will discuss 12 pulse converter. So in HVDC transmission, the series conduction of the converter groups has been preferred because of the ease of control and protection, as well as the requirement of the high voltage rating, right? We prefer to use series connection of converter because of ease in control, right? Then after that, a 12 pulse converter is obtained by series connection of two bridges, right? If we connect two bridges in series, 12 pulse converter may be obtained. 12 pulse converter may be obtained. That means from one converter we will be able to get 6 pulse converter, right? And 30-degree phase displacement between the two sets of the source voltage is achieved by the transformer connection star star for feeding the one bridge and star delta for feeding the second bridge. Bridge 1 will be supplied from star star type transformer, and bridge 2 that will be supplied from star delta type transformer. This is why to achieve 30-degree phase displacement, right? In case of the 6 pulse converter, phase displacement between the two phases is 60 degree, right? Whereas in case of 12 pulse converter, we will be able to achieve 30-degree phase displacement, right? 30-degree phase displacement, because phase displacement is equal to 360 divided by number of pulses. 360 divided by number of pulses. If number of pulses are 6, that means 360 by 6. What is the phase displacement? 60 degree. And if number of pulses are 12, then it will be 360 by 12, 30 degree, right? And how you would be able to attain this phase displacement of 30 degree? By using, because we are having two converter connected in series. To get that phase displacement of 30 degree, because one converter is fed from one particular transformer, right? So bridge 1 is supplied from transformer 1, right? and that is of the order of star type. Bridge 1 is connected with star type transformer. Bridge 2 is connected with star delta type transformer. Why is it so? Because if we are using this type of the transformer connection, we will be able to get 30-degree phase displacement, which is required for 12 pulse converter. Right? The use of the 12 pulse converter is preferable over the 6 pulse converter because of reduced filtering requirement. Right? Because of the reduced filtering requirement. Right? So what this mean? What does this mean? This mean is if we are having 6 pulse converter, then in that cycle of the 360-degree, we are getting 6 number of the pulses. And we will have to filter it out to get the smooth DC output, right? Or to get that pure DC output, we will have to smoothen that output of the 6 pulse converter. But on the other side, if we are using 12 pulse converter, then in that particular case, there are 12 pulse in the output of the converter, and if number of pulses will increase, then filtering requirement is reduced, right? Because interval of the pulses will become small, so we will get approximately constant DC if we are using 12 pulse converter without the help of filter, right? That's why we will prefer to use 12 pulse converter over 6 pulse converter. We will prefer to use 12 pulse converter over 6 pulse converter. Why? Because if we are using 12 pulse converter, then there is no need or no requirement for filtering of the output of the converter, right? And however, increase in pulse number beyond 12 is not practical. We are using 6 pulse converter or we are using 12 pulse converter, right? We may use 6 pulse converter in some of the application, right? And we may utilize 12 pulse converter in some of the application, but the number of pulses beyond 12 is not practically possible because the non-characteristic harmonics are not eliminated, right? Your non that non-characteristics harmonics can be eliminated, but if instead of that 12 pulse converter we are using 18 pulse or 24 pulse, then non-characteristics harmonics cannot be eliminated, right? And this is due to imbalance of the supply voltage, because if we are using 18 or 24 or more number of the pulses, then in that particular case your supply voltage will become imbalanced, and we are not able to control or we are not able to eliminate that non-characteristic harmonics, right? So in case, now see this diagram. In this diagram we are using this diagram to represent 6 pulse converter. First of all, see this. Here, these are 2 thyristors. This is the diagram for 6 pulse converter. Six pulse converter, right? Here it will be your point N. Between the two winding, there is a point N. Now, these thyristor, this is the gate of all that thyristor. This is your 1, 3, and 5, right? This is your terminal A dot, B dot, and C dot. Actually, these are the dotted terminal. Dotted means starting terminal, right? So these are your terminal A, B, and C, and this is your A dash, B dash, and C dash. These are the finishing terminals. 4, 6, and 2, right? So in this case, we are getting your input as VD by 2, VD by 2, right? So if we are using this type of the connection, then in that particular case, transformer utilization can be improved. Transformer, in last lecture, we just define what is transformer utilization. Transformer utilization is the ratio of the average peak inverse voltage to the average DC voltage. That is known as index of the valve utilization or utilization of the transformer, right? This may be improved if we are using this type of the connection in case of 6 pulse converter. In case of 6 pulse converter, if we are using 2 valve groups that can share a single transformer winding, then transformer utilization can be improved, right? And generally, to improve the output, we will prefer to use 12 pulse converter. Beyond 12 pulse converter, it is not feasible due to its practical requirement, right? Now, analysis of the 12 pulse converter. Right. Now, for the analysis of the 12 pulse converter, we had already discussed transformer 1 is connected with the star-star type connection transformer, and transformer 2 is connected with the star delta type connection transformer, right? So this is your supply input. See here. Now this will become, because these are the three winding of the transformer, this will denote the input of the transformer, right? If the either starting or finishing terminal of all the winding will be connected together, then connections so formed are known as star type connection, right? So this is your star type connection. Now here I am assuming that this will be your voltage EA, this is your voltage EB, and this is your voltage EC. In phase A, IA is the current flowing. In phase B, IB is the current flowing. In phase C, IC is the current flowing. Now this is the star type connection of the transformer 1. Right? Now, in the similar manner, transformer 2 is also connected, primary is also connected in term of star. Now, this may be connected here. This is connected with the same supply. See here, all that three that will be connected with same input. A is connected with first phase, B is connected with second phase, and C is connected with third phase of the transformer 2. Right? Now, here, this will be, here I am denoting this with IAS, IBS, and ICS, because of this transformer 1 is of the star type connection. Now for the second, I am using the notation IAD, IBD, and ICD. Right? IAD, IBD, and ICD, that are the current in the primary of the transformer 2. Why we are using that star and star delta type transformer? To achieve 30-degree phase displacement. Right? Now here, this secondary of the transformer 1, this is again connected in term of star. So see here, this is the your star type connection, and these are connected with the bridge 1. Right? These are connected with bridge 1. So here I am assuming that current will be, here you may take the notation as IAS, IBS as capital, and here you may take the notation IA small s capital, then IBS, ICS. Right? This will be connected with bridge 1. Then secondary of the transformer 2, that will be connected in term of delta. This is your coil 1, coil 2, and coil 3. Right? Delta means finishing of the first is connected with starting of the second. Finishing of the second is connected with starting of the. Finishing of the second is connected with starting of the third. Finishing of the first is connected with starting of the second, and finishing of the third is connected with starting of the first. Now this will become delta type connection. Finishing of the first is connected with starting of the second. Finishing of the second is connected with starting of the third, and finishing of the third is connected with starting of the first. Connections so formed are known as delta type connection, right? And now these are connected with output of this winding is connected with bridge 2. Here you are getting VD1 and here you are getting VD2. VD1 and VD2, and these two are connected in series with each other. So here you will get ID. This is the diagram for 12 pulse converter, connection diagram for 12 pulse converter. So this diagram is for the analysis of the 12 pulse converter, right? So see here, here are two transformers. This is your transformer 1 and this is your transformer 2. This upper one, this is your transformer 1 and this is your transformer 2. Right? Transformer 1 is of the star nature and transformer 2 is of the star delta nature. Both are supplied with the same input, right? Transformer 1 is used to supply the bridge 1 and transformer 2 is used to supply the bridge 2. We are using transformer 1 as a connection star type and transformer 2 as a connection of star delta type to get required output for the 12 pulse converter and phase displacement of 30 degree. The current IBD flowing in the primary winding of the star delta connection transformer now see here I am assuming this is your current I1, here it will be I2 and here it will be I1, I2 and I3, I1, I2 and I3. These are the current in winding 1, 2 and 3 of the star delta type connection. IAD, IBD and ICD is the current supplying by the transformer 2 to the bridge 2. Transformer 2 supplies the current IAD, IBD and ICD across the bridge 2. Now, in first case, here you may note these notation as IAD, IBD and ICD as the capital, right? So here, because of the connection IAD, current IBD flowing in the primary winding, IBD flowing in the primary winding of the transformer 2, flowing in the primary winding of the transformer 2, which is connected in term of star delta type, is given by root 3 of I2 See here, it in phase 2 of the delta type, I2 is there. Here it will be IBD. This will be in star. This will be in delta. So IBD is equal to under root 3 times I2, right? Where I2 is the current flowing in the secondary winding that is coupled with phase B. Right? Now, we are assuming that I1 plus I2 plus I3 that is equal to 0 under balanced condition. I1 plus I2 plus I3 that is equal to 0 under the balanced condition. So this shows that IBD is equal to IBD is equal to 1 by under root 3 I small bd minus I CD right. These are the equation related with the primary winding current and secondary winding current of the various transformer. Now in the analysis part, I am just going to draw that waveform for the various current IBS, wave shapes of the current IBS, IBD and IB. First, I am just going to draw for IBS. Now, in case of the IBS, you will get the constant output of the value ID from minus 60 degree to 60 degree, right? And from minus 60 to minus 120, it will be 0. And after minus 120, there will be again a negative pulse of the value minus ID. Right. Now, on the positive side, again from 60 degree to 120 degree, 60 degree to 120 degree, the output is 0, and after 120 degree, you will again get minus ID. Fine. Now, this is the diagram for the first case, that is IBS. This is the diagram for IBS. Now, for the second, that is IBD. On this axis, I am taking theta. On this axis, I am taking IBS. Here it will be IBD. Right? Now, in case of the IBD, it is to be noted that IBD and IBD lags IBS by 30 degree, and ICD lags IBD by 120 degree, right? So here you will get two steps. Here let us suppose you will get the 30 degree, minus 30 and 30 degree. Here it will be again minus 30 and 30 degree. Here it will be somewhere 60 degree, minus 60 degree. Now this will be from minus 30 to 30. We are getting the constant output of the value 1.154 ID. 1.154 ID. And after this, from minus 30 to 60 degree, you will get 0.577 ID. Here it will be 0.577 ID. These are hypothetical value. So 0.577 ID. So see here you are getting the constant in case of IBS. Here in case of IBD, this will be with some ripples, right? This wave shape will be again repeated in the negative cycle like this. Here it will be again repeated in the negative cycle. So this is the wave shape for IBD. Now IB, this is IB is equal to, this is the sum of upper two wave shape, right? So IB is the sum of upper two wave shape. So you will get, here it will be 1.154 plus 1. This will be 2.254 ID, right? Then after that it will be 0.577 plus up to this 1. This will be 1.577 ID, right? And then after this, here it will be 0.577. This process will continue like this. So you will get more number of the ripples in case of IB. In case of IB, you will get more number of the ripples, right? So it is to be noted that IBD lags IBS by 30 degree, whereas ICD lags IBD by 120 degree, right? Now, as far as that RMS value of the fundamental component is concerned, RMS value of the fundamental component of supply current in 12 pulse converter, that will be given by RMS value of the 12 pulse converter is equal to 2 under root 6 by pi ID. This is your value of I1. RMS value of the fundamental component of supply current in case of 12 pulse converter, that will be given by I1 is equal to 2 under root 6 by pi ID, right? And harmonic current IH, harmonic current, this is the fundamental component of the current. This is what fundamental component of current, that is given by I1 is equal to 2 under root 6 by pi ID, whereas if we are talking about harmonic current IH, harmonic current IH is given by I1 by H, where I1 is equal to 2 under root 6 by pi ID, right? Here H is equal to, because we are using 12 pulse converter, so H, where H is equal to 12n plus minus 1. H is equal to 12n plus minus 1, where n is a integer, or this may be where n is any integer, right? Or this may be equal to 6m plus minus 1, where m is any even integer. M is any even integer. Both of these harmonics are same value. So in comparing with the harmonic current of 6 pulse converter, it is obvious that the 5th and 7th harmonics flowing in two transformer cancel each other, right? In case of 12 pulse converter, if you see, the 5th and 7th harmonic component of the two transformer cancel each other, right? And this can be generalized to the case whenever m is an odd integer, right? If you compare the harmonic current with the 6 pulse converter, if you compare the harmonic current of the with the 6 pulse converter, it is obvious that the 5th and 7th harmonic flowing in the two transformer cancel each other, right? This can be generalized to the case whenever m is an odd integer, right? So these currents, these wave shape represent the different component of the current. Yes. For all this analysis, whatsoever we had covered, it is assumed that whether it will be transformer 1 or transformer 2, both are having the turns ratio as 1:1, right? It is assumed that both of the transformer, that means transformer 1 is of the order of star type, transformer 2 is of the order of star delta type, right? It is for all this derivation or all that analysis part, it is assumed that transformer are having the turns ratio as 1:1. What is transformer ratio? Transformation ratio, it is the ratio of the number of primary winding to the number of secondary winding turns. number of primary winding turns to the number of secondary winding turns, or it is equal to ratio of the ratio of the primary induced voltage to the secondary induced voltage, or if you will see in term of current, it will be in reciprocate. That means it is equal to secondary winding current to the primary winding current, right? That means that transformation ratio is equal to V1 by V2, and that will be equal to E2 E1 by E2, and it is equal to I2 by I1, where I2 is the current flowing in the secondary winding and I1 is the current flowing in the primary winding, right? So for this analysis of the 12 pulse converter, it is assumed that that means both of the transformer 1 and transformer 2 are having the turns ratio as 1:1. That means number of turns of the primary winding and the number of the turns of the secondary winding are equal, right? For both of the transformer, number of turns of the primary winding and number of turns of the secondary winding are equal. And on the other hand, you may say that whatsoever input voltage is applied across the primary winding, we are getting the same across the secondary winding because of the turns ratio 1:1, right? Next, we will see effect of the smoothing reactor, right? So till now it was assumed that ID is constant, right, which implies that reactance of the smoothing reactor is very high. Reactance of the smoothing reactor is very high. That means ideally we may say that it is very high. Theoretically it will be infinite. Ideally it will be assumed to be infinite, right? So if the smoothing reactor is finite, then we cannot neglect the ripple in the DC current. We are using this smoothing reactor to remove the ripple, right? To remove the ripple in the output of the bridges, right? So here, let us say here it will be your 12 pulse converter, and here it will be your smoothing reactor. Smoothing reactor is connected, right? This will be, let us suppose, ID is the current flowing through it. Here it is having the voltage as VD. This is the equivalent circuit for calculating the ripples. To calculate the ripple in the DC link current, consider this circuit. Now LD is the value of the inductance. LD is the inductance of the reactor, and VD is the constant voltage source that represents the effect of the converter at the other terminal, right? The time varying voltage VD of T, time varying voltage VD of T, this is equal to EM cos omega T. VD of T, that will be given by EM cos omega T for the time period minus pi by P to omega T minus pi by T plus alpha to omega T to pi by T plus alpha. In first case, this will be minus pi by P plus alpha. Then in second case, this will be pi by P plus alpha. Right. Now, because the losses in the circuit are neglected, so we have the constraint that is given by VD is equal to this integration of, first of all, P by 2 pi integration minus pi by P plus alpha to pi by P plus alpha VD omega T. VD d omega t, because here VD is variable with respect to this omega t. So that's why we are taking this integration with respect to alpha, right? So if you will substitute this value of the VD is equal to EM cos omega t, then value of the VD may be calculated, and then by the use of that VD, you may able to calculate that value of the current through the bridge, that is ID, right? Although in simple word, it is assumed that smoothing reactor is used for removing of the removing of the ripple or to smoothen the output of the bridges, right? So this is the end of the lecture. We will meet in next lecture again. Thank you.
Thank you, sir.